All right, I'm going to go ahead and get started because it is 8:05, and yes, we're probably all really tired after using some time over the break to catch up on sleep, and now having to get up and watch the lessons. But we're continuing on with section 3.1. We've already spent a couple of days on this, so we have to finish this up today. And we're writing and using exponential and logistic functions, graph and transform exponential and logistic functions, understand and use the natural base E, and then use exponential and logistic functions to model population growth. So these are all of our objectives, and every problem really has a mixture of these in it. It's not like we can say, each problem. Number 2 will cover understand and use the natural base E. Everything is kind of linked together. And we were at example 6, part B. Which might be down here. Wow, we really did get through quite a bit of this. So here we are. Example 6, graphing logistic growth functions. And this is a large chunk of knowledge that was just supposed to get us to see this is the kind of thing we'll see with logistic functions. So graphing logistic growth functions, we graph the function, find the y-intercept and the horizontal asymptotes, but we also want to focus on that point of the greatest amount of growth, which is the inflection point. That's going to be something that helps us graphically and in answering questions about when is the greatest growth happening. So with this one, we've got g of x for part B, because we covered A before the break. G of x equals 20 over 1 plus 2e to the negative 3x. And we'll notice some differences between A and B. The big one is that we have this numerical base of 0.7 to the x in the denominator for A. And in B, we're now using e, which is that natural base. And really, with population growth, you do see the use of Euler's number quite a bit more than you do with just normal numerical bases. So we've got g of x equals 20 over the quantity 1 plus 2e to the negative 3x. And one of the first things we would want to do is figure out where those asymptotes are at. And we talked about how y equals 0 is definitely going to be our lower limit, and our upper limit will come from this 20 that's on top, which our book has designated as C. So that will be the upper limit. So we want to get those on our graph. And the first thing to do with B would be, well, let's take a look at what they said we have. The x's are going from negative 2 to 4. So they must be going by ones. Negative 2, negative 1, 0, 1, 2, 3, 4. And we can get those labeled. And then our y values are going to go from negative 5 to 25. So that looks like they're going by 5s. And before we find any points that are on this graph, we should put those asymptotes on. That's really important. Well, with any of the graphing that we're doing, the asymptotes are really important, but especially with these. So there's our y equals 0 and our y equals 20. And now we'd want to know some points that actually are on the graph itself. And we could start with the y-intercept. And remembering that anytime you graph on the y-axis, it has the coordinates 0 and then some number. So that means we want to put a 0 into this function and see what we get. Well, negative 3 times 0 will be 0. Anything to the 0 power is going to be 1. So 2 times 1 is 2. 1 plus 2 is 3. We'll get 20/3. Now to graph that, we probably want to think of it as 8 2/3 when we're doing this with the mixed number. So let's go ahead and put on the one point that we do know, the 0, and then 8 2/3. Sorry, 6 2/3. Somewhere there, about there. But that's not enough to get our logistic graph in there. So what we have to do is figure out what other points would be really helpful. And that's going to be this inflection point. So I have to remember that the inflection point always comes from taking that upper limit and dividing it by 2. So for my inflection point, I have to take 20 and divide it by 2, and that'll give me 10. But I don't know what the x-coordinate is yet, so that's where we have to do a little bit of algebra. We have to set g of x equal to 10, and then we have to solve to figure out what x is. So we'd multiply both sides by 1 plus 2e to the negative 3x, and that'll give us 10 times 1 plus 2e to the negative 3x equals 20. And then instead of distributing that 10, it's probably easier to just divide both sides by 10. Then we'd subtract 1 from both sides. Divide by 2. And then we have to remember how to get rid of the natural base e. And when we have a power being raised to, actually a base being raised to an unknown power, what we have to do is think, how do I get to this x? And the only way to get to that x is to eliminate that e. And we're going to have to take the logarithm base e of both sides, which is natural log, and that will give us, because these two are inverses of each other, they'll cancel out. Negative 3x equals the natural log of 1/2. And then all we have to do is finish up by dividing both sides by negative 3. So this we would punch into the calculator and we'll figure out what x is. So natural log of 1/2. And then we'll divide that by negative 3. And we get about 0.231 to our 3 decimal places. And again, that's a really important point. That's our inflection point. So that's where our curve is growing the fastest at 0.231, so not very far over on the x-axis and up 10. And then just like we did before we left for break, we said, well, let's just use that for symmetry because these are always symmetric around that inflection point. So you just kind of eyeball from the point that we had for the y-intercept to that inflection point and say, well, this one's not going to go real far over. We're looking about like that. So this isn't necessarily what we would call graph on a test. It's more of a sketch of what we need to get everything on there. And if we did need to graph it on the test, we could certainly put this into the calculator and we could get some really nice numbers, really nice decimals from the table. But with these, we have to remember that if there's more than one term in the numerator or the denominator, you're going to need parentheses. So this would absolutely require some parentheses for our denominator to do this. Most of the time, because we're looking at these as that part of our objective that talks about population growth, what we want to do is look at these on a calculator and start answering some questions about it. And that's what we're going to do in extra example 6. So when our last objective was talking about using exponential and logistic functions to model population growth, that's exactly what we're doing here. This one says, a horrible rumor begins to spread through a population of 2,000 students. After T days, the number of people who have heard the rumor is modeled by the logistic function. R of t equals 2,000 over the quantity 1 plus 115 e to the negative 0.97 t. And like it says, we want to graph this in an appropriate window. We want to make sure that we can see the entire S curve that we're looking at. So we'll have to be careful and make sure that we're using parentheses in the denominator. You know what? You can't go wrong by always using parentheses for the numerator and the denominator. So it's up to you whether or not you want to put in the extra parentheses or not. But the first thing that we want to do is get this in the calculator and take a look at it. So on the top, we had that 2,000 for our numerator, divided by, and don't forget to use the parentheses there, 1 plus 115, and then we have to call up that natural base feature, which is e to the x, and that's going to be second ln, and we need negative 0.97, and we'll use an x, arrow it over once to kick it out, and then to finish up those parentheses. So now, the key to this is going to be figuring out what the window is, because I'm going to hit zoom 6, and we're not seeing that full S curve. So we think, well, what are we supposed to know about the X's and Y's for this? And we know that our horizontal asymptotes will be at 0 and at 2,000. So for our Y's, that sounds like a good thing to use. 0 to a little bit more than 2,000, maybe 2,050. And our T, which is our input, so that's our X on our graphing calculator, is after T days. So you start to think, school with 2,000 students, about how many days would it take for almost everybody to hear this rumor? Well, let's just try, because rumors spread pretty fast. 0 to 10. And again, we know that our horizontal asymptotes are from 0 to 2,000, so we've got to take a look at a little bit higher than that. And you could put a few negatives in if you wanted to. But now we can see the full S. And if you're thinking, you know what, I just want a little bit more of that, I want to see that, well, just make your X's a little bit bigger. That's what we want to see. We want to see that S curve. So let's go ahead and just make a sketch. Knowing that y equals 0 is one of our asymptotes, and y equals 2,000 is another one. And let's see, starting at that 0. And that should be good enough for just a sketch to say, hey, this is what we saw on our graphing calculator. Now, A says, how many people originally heard the rumor? Oh, well, that's interesting. So they're suggesting that maybe it just wasn't one person talking to another person, that there might have been a group of people standing around. And that's all part of our objective of understanding the population growth. So if I take a look at this one and I think, well, it started when time was, I guess, 0. That's when everybody was standing around and they were talking about this. So it would be 2,000 over 1 plus 115, e to the negative 0.97 times 0. Well, this is going to be to the 0 power, and anything to the 0 power is going to be 1. So 115 times 1 is 115, And we'll have 1 plus 115, which is 116. So 2,000 divided by 116. So about 17 people. We don't want to say 17.241 people. That doesn't make any sense. So about 17 people. So that tells us, obviously, these people were all together in one spot for one reason or another. You know, maybe it was a locker room situation or something like that, but they've heard the rumor at the same time, and this is when the rumor started. So how many people heard the rumor? About 17, because we're rounding to that nearest whole person. B says, find the number of people who've heard the rumor after day 1, day 2, 5 days, just to get us to see what's happening with that growth. And my first thought is, well, that's what we see when we're working with the table. So maybe we'll just do 1, 2, 3, 4, 5, and 6. And we'll round those to the nearest person. So second graph. And there's our 17 again. So we'd write down about 45, 114, 275, 593, 1,053, 1,491. And that gives us a good feel for what's going on with those numbers. And I know I have those written down so that I don't have to put this into another calculator so that I could see it. So there it is. Now, C says, hey, we're still picking away at that objective where we want to figure out how does this work for population growth. How many people have heard the rumor when the rumor is growing the fastest? And on which day did this occur? Now, what they intended was that we would see in part B, hey, look at when this growth really kicks up here. But that's not how we're going to find that fastest growing spot. Can anybody remind us, unmute yourself and remind us what the special name for that spot of biggest growth is, please?
The inflection point.
Thank you. That's exactly what it is. So I go back up and I think, what was that upper limit? It was 2,000. I'm supposed to divide that by 2, and that will give me the y coordinate for the inflection point. So I need this to equal 1,000. Now, since I already have this in my graphing calculator, this would go a lot faster just by figuring out, using the graphing calculator, where is that y value 1,000. So I can go back up into y equals, and I can make y sub 2 equal to 1,000. And I can see very clearly that this is going to be my inflection point right here. So I'll let the calculator find that for me with second trace and then number 5 intersect. And since these are the only 2 curves I have in here, I can just go ahead and hit through first curve, second curve, and take a guess. And here I see it's going to be 4.892 to 3 decimal places. I'm just going to write, for the people that watch the video, GC here. We used a graphing calculator and we put that in as y sub 2. So, and I think, well, does that make sense? Does 4.892 make sense in this situation? Well, 4.892 was about time. And this is just a rumor, so we'd probably want to say about 5 days. If they want to know specifically, yeah, we could break this into, you know, 4 days and then figure out the 0.892 of the next day. But for a rumor, we're probably just going to say it's going to be about 5 days. And then we'll have those 1,000 people growing the fastest at our inflection point. D says, describe the end behavior of the graph, and what does this mean in terms of the rumor? All right, so we want the limit as, and they used t, so let's stick with that. T approaches negative infinity, and they called this one r of t. So we always want to make sure we're using the correct notation. This just goes all the way back up to the front of the page, or front of the page, top of the page, where they called it r of t instead of sticking with f of x, and they use t for time. All right, so we've got 2 little blanks to fill here, describing that end behavior of the graph. But we should already know where these are going to be. Can somebody tell me what we should be putting in here for the limit as we go to the left forever?
0.
Right. 0 is going to be our horizontal asymptote as we're going to the left forever. And then can somebody please unmute and tell me where this is going to go as we go to the right forever?
2,000.
Exactly. So, what we're really saying here is we had to start with somebody hearing the rumor. You know, it can't be 0. Somebody had to hear the rumor for it to get started. And then it's not going to reach all 2,000 of the population, because every once in a while there's somebody that says, no, don't tell me that. Rumors, I don't do rumors. It's gossip, and I don't want to hear gossip. Or it could be that somebody's absent during the period of time when this rumor was being spreaded, and so they just never heard it. So we know that this is not going to be a perfect model for how that rumor is spreading, but it's going to be awfully close, and that's what we're looking for when we're studying these logistic graphs. So we had a huge chunk of information about the logistic graphs that we were doing, and this last one really gave us a look into how do you analyze everything that's happening with the graph in that word problem. And we have another one here that's saying using exponential and logistic models for population growth. And that reminds me, didn't really do an exponential one yet. You know, we've been talking about the logistic growth. So this star up here gives us a really big piece of information about the census. So a note on population. It says when the U.S. Census Bureau reports a population estimate for a given year, it generally represents the population at the middle of the year, which is July 1st. We will assume this to be the case when interpreting our results to population problems unless otherwise noted. So then you start to think, well, wait a second, that's halfway through the year. And we have to think about that as we do these problems. So halfway through the year. Because July is the 7th month, you've already taken care of everything through June, which would be 6 out of the 12 months on the calendar. So example 7 says modeling San Jose's population using the data in table 3.5 and assuming the growth is exponential. When will the population of San Jose, California surpass 1 million persons? Well, the first thing to do would be to think, okay, how do we set up an exponential model? And I'm going to go ahead and call it f of x since it didn't give us specific names that they wanted here. Actually, let's go with P of X because it's a population model. So we'll go with P of X just to give it some content specific information. And then we want to figure out, well, what do I do about this a times b to the x? You know, how am I supposed to figure out what those numbers are? Well, remember, a is always, what did this start at? So let's go take a look over here at table 3.5, and it says, starting to collect data in 2000, it was 898,759. So that's our a value. The part that we have to spend a little bit of time on here is figuring out, so what was b? So I have to think, what do exponential models look like? So in 2000, they started off with some number. I'll just call it y. And then for 2001, because this was an exponential model, they had to take it times b, whatever b was. Well, then they had to do that again. And again, and again, and again, because that's what happens with an exponential model. When we're increasing this x model by 1, we're saying we need to multiply by that base one more time. That's what powers do. So from 2000 to 2007, they went through that 7 times. So they took 898,579 times something to the 7th power, and that gave them 939,899. Well, that we're going to have to solve because we have to figure out what that x is, because that x is actually our base. So the first thing we would do is divide both sides, and I'm going to change this now to b to the 7th. So we're going to divide both sides. And then we have to figure out, how do you undo raising something to the 7th power on a calculator? And that's going to be 7th root. So we haven't had to do that in a long time. I want to make sure that it looks like my root goes over the whole thing here. There we go, all the way down. And that's our math button on our calculator. Uh-oh. And my calculator decided to close. When I was moving it over, I must have accidentally hit a little red button on the calculator. There we go. So if I want 7th root, I have to hit 7 on the main screen. So I'm going to get out of the graphing there. 7 math, and then I have to go down to number 5, 7th root of, and then we had that big monster 939,899 divided by 898,579. Double check that I've got all those numbers in there right. And enter. Now, with these, thousandths position, 10,000ths position can sometimes make a big difference when you're talking about really large numbers. So we usually think about these in terms of 3 significant digits, not necessarily talking about, just 3 decimal places. Zeros are not considered significant digits because they're just placeholders. So it would be best if we went to 1.0064 and use that for our base in this particular problem. Now, if you use 1.006, You'll be okay. You just won't have quite as accurate of data as somebody that's sitting next to you that used the 1.0064. So we've got to get that on this piece for P of X up here, 1.0064 to the X, T. I mean, if you make this P of X, then use an X for your power up here. If you want to use P of T for time, then make sure that you use T up here. But there's our model. And it says solve graphically because we were supposed to figure something out about this. What we had to figure out was, when will this surpass 1 million people? Well, we certainly could just put 1 million over here for P of X. And solve it algebraically using logarithms. You can divide both sides by 898,759 and then take the logarithm of base 1.0064 to finish it up. But we want to see what this model looks like as well. So let's go ahead and put it in the calculator and see what happens. All right, so we had 898,759. And I'm going to go ahead and put my base in parentheses here. You wouldn't have to. It'll take it either way. So there it is. Now, we want to see the window. And we're talking about the number of years. So I think I'll just stick with 0 to 10 years. In 2007, remember, we were at 939,899. So if that's the 7th year, we might be able to hit that before the 10th year. And we have to be able to see a million, so maybe I'll put in 1,100,000. Did I get enough zeros? I did. So there it is. Now, it's going up. We can see that increase. I want to know, when is this going to hit a million? And my out to 10 years there was not quite enough. So, window, let's try 20. And now I can see where they intersect. Second trace, number 5. Enter, enter, enter. 16.73 is what we get for X. Now, here's where that starred information up in the upper right corner comes into play. We have to remember that this was collected halfway into the year. So if we want to get a correct answer on this, we're going to have to add half of a year to that to see when this is going to happen. So we'll get X equals, and this will be 3, 2, 17.23. So we could say in approximately 17 years, early. But they wanted to know when this was going to happen. So that means in terms of years, what year would it be? Well, the good news for that is it started in 2000. So all we have to do is take 2000 plus 17, and we would be saying sometime in 2017. In fact, we could just say sometime in early 2017, because 17.23, so 17 years and then 23/100ths of the way through the next year. So this one used something we haven't used in quite a while, and that's going to be our 7th root piece on there. So a big part of our objective was knowing not just the logistic, but also knowing those exponential growth models, and that's what we did there. So example 8 says, modeling Dallas's population. Based on recent census data, a logistic model for the population of Dallas T years after 1900 is as follows. And we see this base of E again in a population model, which, like I mentioned earlier, that happens a lot. According to this model, when was the population 1 million? Well, that would go over here. So we have a couple of choices. We could definitely solve it algebraically. You're going to see this has a lot of nasty decimals and things in it. Or we could punch this into the calculator. And it's a really good habit for us to at least do 2 of these logistic functions so that everybody remembers that you have to have parentheses when you put these things into the graphing calculator in order to get it to graph accurately. So there's our census data. We're going to put it into the calculator. I will probably put this in as my y sub 1 and this in as my y sub 2 and see when they hit each other. All right, so backing up here. 1,301,642 divided by, and you'll notice I didn't use parentheses on the top this time, and that's totally fine. Either way, use parentheses or don't, it'll give you the correct answer, as it'll follow the order of operations. And then on the bottom, we have to use parentheses for our 1 plus 21.602. And then we have our natural base E, second ln. And here's where we have to be careful about all the decimals. Negative 0.05, 054, and then my x. Pop it out and put the parentheses in there. I'm going to double check my decimal there, negative 0.050554x. We've got it. And the window. 0 to 20 years, probably not a bad idea. And then we have to be able to see 1 million again. We won't be able to see the whole graph if we just go to 1,100,000, but we don't need the whole graph, so let's try graph. And let's go back and put that 1 million in for y sub 2. And boy, we've got a ways to go. I mean, this is going to take a lot of years to get this up to the 1 million. So in our window, let's try 0 to 100 years. And now we're getting almost the full S look, but we can definitely see where we're going to have that intersection. So second trace, number 5, enter, enter, enter. 84.513 years later. Now, this was again based on census data. So we have to catch that when we read through these, and that'll help us figure out, okay, how many years are we really talking about? Because this was collected halfway through the year. We know this is going to be sometime in 85. So we could say something like in the beginning of 1985 or early 1985. Because this data started in 1900, and this time this information wasn't given in tables. It was given in the words of the problem. So census data tells us we have to use the 0.5. T years after 1900 tells us, hey, that's our 0 year. And so sometime at the beginning of 1985, we'll get all of that. So this section took us 3 days to make our way all the way through all those objectives and see every chunk of information that we had to know about our exponential and logistic models. And now you'll definitely be able to finish up 3-1 day 2. So 3-1 day 1, you should have been able to finish up with what we had before the break. We just need to add a little bit more to 3-1 day 2 so you could get through the word problems down there. But we've covered all those objectives that we had, and yeah, you could definitely rate yourself after the lesson, and then after you do the homework, think again about, where are you at? How do you feel with all this population growth? But that is a good place to stop today. I thought about maybe going into the next section, but I think it'll be good to finish this one up and get everybody's brains back into thinking about what we were doing before the holiday break. So again, feel free to stay on and work and ask questions as they come up, or go ahead and work, and you can come back anywhere within, I guess, the next 8 to 10 minutes here if you need to. Have a good day, everybody.